part of our optimization talks. In this one here, we're going to really touch upon a couple of sort of miscellaneous items, primarily return value optimization, and then having a look at inlining. We'll start off with return value optimization. This follows on from the last talk where we were having a look at temporary variables and L values and R values. Then that there's a danger when we are calling methods or performing computations that we may end up generating R values that get to incur a creation and a destruction cost, but other than that are very, very short-lived. And the return value optimization is one way of that a compiler can use to more efficiently handle this situation. So by way of reminding you of the context, if we have a look at the fragments of code over on the right-hand side, we have a class called foo. One of the constructors of foo takes in an integer. And we're imagining here a method which will create an instance of foo given a particular parameter, and that is then returned. And for sake of argument, okay, you're likely to have more sophisticated code within it, but let's say at some point we actually are returning a new instance of foo. And at the very bottom then, we are creating an instance of foo and assigning that equal to whatever create foo returns, passing in the parameter. So if we think about what may happen here, so we call create foo first of all. It then calls that method. Within that method, we actually create our temporary foo object by directly initializing it using the A value that's passed in. Now that's an R value. It's an object that exists, but we cannot refer to it by name. It's a temporary variable. That's then returned from the method by value, and we then potentially call the copy assignment constructor to copy the contents of that R value into our foo instance. So this was the thing we wanted to avoid, because there we are creating an object and discarding that object really unnecessarily. And what the return value optimization technique, and this is a technique that compilers can use, is that if it sees a situation where this is happening, where we're creating, instantiating an L value, some named variable, and we're using an R value to do that, then it substitutes the L value for the R value. In other words, that effectively whatever is returned from create foo is actually foo itself, or variable foo. So it doesn't do the copy, it just says, okay, let's create this, we get it returned from it, and let's just then call it by whatever L value name that we are using. And that avoids then the need to perform that temporary creation and copy. In general, there are some sensible guidelines as to how we would use this. So the example at the top is a safe one. So we're creating a couple of strings. In line 3, similar to the one we see in the last slide, we're concatenating them, and we're then assigning that equal to S3. Structured as such, this is a good compiler, will result in RVO kicking in, and there'll be no temporary R value created. The one underneath, though, is more problematic. In this one here, in lines 1 and 2, we're still creating our first and second strings. In line 3, however, we are actually creating an instance of the S3 string. So that will result in the default no argument constructor being called. And at line 4, because S3 already exists, it exists prior to that. In this sense here, S1 plus S2 will result in a temporary variable being created, and then the copy assignment constructor being called to copy it across. So you should favor the form shown at on the top, where we defer creation until such a point that we can directly construct the object, and then that is what we should do, as that's more likely to be efficient in terms of object construction. A couple of general pieces of advice or asides on this, because here we're talking about passing things into methods or returns from methods. When we are calling our methods and we're passing in parameters, for example other objects, we should be careful here. This is less of an issue in Java in particular, because everything is passed by reference, but in C++ you get to choose how it is passed. And if you have an instance of a class and you just pass it in, then passed in by default, by value, and that's not a good thing, because it means, probably not a good thing, depends on how you're using it. It means then we're pushing a lot of data onto the stack, and that's maybe not as efficient. So general, where if we are calling objects and or methods, and objects are part of their parameters, we normally want to pass them in by reference. Reference is a good choice, is better than by pointer, because we can be sure to have a non-null reference that definitely points to the object. Alongside that, and this is good coding practice, if the method that we're writing, it doesn't modify the argument, then we should declare the method signature to have a const parameter, so that it is clear to the callee that whatever is passed in, be it an object, it isn't going to be one that this object, this method will modify. Good thing to do, makes it clear to the callee in terms of what role this has, and it avoids those potentially ugly use of a const cast. If the callee knows, okay, yes, it actually doesn't modify it, but it hasn't been explicit in terms of its formulation. The last thing we want to look at is inlining. And we'll see from the diagram here, sort of suggesting inlining is similar to the notion of copying, and we'll see that's going to be the heart of it. To have a look at inlining, we need, by way of understanding the context, we have to have a look at calling a method and what happens whenever you call a method, and provide a little bit of a breakdown of some of the key things, the key steps in the process of invoking a method. So similar to using the new keyword, whenever you call a method, various things happens behind the scenes by way of orchestrating that method call. And I've highlighted a few of them. So let's look at over the left-hand side. We've got the instruction pointer. For executing your program, the instruction pointer base is a pointer, it's a raw pointer, and it points to the next instruction or the instruction in memory that you are executing. So effectively, this points to the bit of memory that contains the code to be executed. Obviously, if we're calling another method, then we have a break in that. We are likely to be jumping to another piece of memory and pointing to that bit of memory that contains the code associated with that method. And when that method finishes, we want them to jump back just to whereabouts we were so we can carry on executing the next instruction in line. So the instruction pointer is the one that enables us to know which bit of code we are executing. When we call a method, we have to record to remember that instruction pointer, and that's done quite often using the link register. And we then have to update the instruction pointer so that it points to the executable code associated with that method. The link register, then, the bit in the middle. So this gives us the address that we return execution to whenever a particular method has finished. And if you think about recursion, where one method calls another method calls another method, it means that we just can't have one link register. We need to have a way of being able to have a series or a stack-like structure of them. And unsurprisingly, for link registers, these are items that get to be pushed onto the stack as part of that method call. So if I call a method, I'll push onto the stack the link register where I should resume from or resume to after I finish that method. If that method itself calls another method, then as part of that method invocation, I'll push on a new link register so that I can, if you like, chain my way back up until the first call. Stack pointer is another item here that needs to get managed. So when we're calling a method, we're going to use the stack for holding a lot of these different parameters. Stack pointer is a pointer that tells us, well, what is the next bit of the stack that is free. So every time I call a method, effectively I am allocating or using a chunk of the stack, and I move my stack pointer forward. The nice thing about the stack, or one of its required uses, is that it should be very quick to allocate and deallocate data. And the way that's generally done in the stack pointer is that when you're calling a method, you record what the previous version was, if you like, the version or the bit of memory you were pointing to before you called that method. You then update and you reserve chunks of memory on the stack for whatever method you're calling, and that gives you a new stack pointer. But if you remember where the old location was, it means that whenever you exit out of that particular method, you just need to go back to wherever the old pointer pointed to. So it gives you a very quick way of then freeing up the allocated memory on the stack. So instruction pointer, link register, stack pointer, these are all routine things that we will generally use by way of helping us execute our code. Side at the bottom, there's lots of other things depending on the environment and how code gets to be executed, but I just want to highlight here that behind the scenes there's a number of steps that happen. On the other side, whenever we, we'll look at it sort of both ways. So this one here, first of all, we'll have a look at the series of steps we would go through to execute a particular method. And then we'll have a look at it in terms of what we do by way of returning. So here's a few things which are likely to kick in. So we call a particular method. We're calling a method. The method might have arguments that need to be passed into it. How do they get to be passed in? They get to be pushed onto the stack. So anytime we invoke a method, we will go to the stack, we'll make sure that if we have a couple of integer arguments or a pointer argument or whatever, that we reserve notionally memory on the stack. We update the stack pointer, so it points to the first argument. We then push those values onto the stack, and that's notionally, if you like, our arguments passed in. Having done that, we then want to record where it is we return to when that method finishes. So we store in the stack our current instruction pointer, and becomes then our frame reference. The method that's called, now this comes down to how things are implemented and particular ways done. We might have a method that uses a number of different registers in the processor. It's generally good if a method sort of looks after and is clean by way of its execution. So sometimes the method will be storing other registers on the stack, and it pushes just the values onto the stack as well. But all of this setup happens before we finally update our instruction pointer to execute the code associated with that method call. And that method call then knows to go to the stack, look at the stack pointer for finding its arguments. When we've finished execution and we want to return back, there's a number of really steps we're doing here, and to a certain extent we're sort of working our way backwards at this. In the same way we can pass arguments in, we can also have a return value from a method. How does it get to be returned back to the callee? You've guessed it, we push the thing onto, for example, the stack. We're storing it so it's accessible whenever we return. All the registers, if we saved any registers, we need to restore them back to their original state, things like the stack pointer, frame pointer, and so on. We then check for the previous instruction pointer, the one we stored in the stack, where it is we jump control back to. So we back out and we then return to normal execution. Now, all of that's interesting enough, and it'll differ depending on the environment. The key takeaway from this is that if you invoke a method, it is not something that happens for free. There is a cost associated with calling and then returning from that method. And depending upon the number of arguments you're passing in, it could be from maybe 25 CPU cycles, 100 CPU cycles, but there is a body of work to be done. This is relevant because if you have a method that you call frequently, and inside that method, it only does a little bit of work, it means then that you might end up doing, let's say, 20 cycles of actual useful work, but alongside that have a cost of maybe 50 cycles of calling it in the first place. And if you do that frequently, it means that most of your time has actually been spent up calling and getting back from methods, and relatively little time in terms of doing useful work that ties in with whatever you're trying to achieve. This is where inlining comes in, or the notion of inlining. C++ actually has an explicit keyword for it. What inline suggests is a hint to the compiler. It says that I recommend that this method is inlined. Now, if something is inlined, it isn't actually called. And any time you see an invocation to that method, what happens is that effectively you mostly copy and paste the contents of the method directly into the code. So it avoids calling the method by directly inserting or injecting that code into your code base. It's faster, it avoids the execution cost, but the price, the penalty you pay is that you're making your code bigger, because you're not just having one set of instructions, you're pasting it in multiple times depending upon the number of times that you call it. Within a loop it's only going to be pasted in once, but the number of discrete instances at which it is invoked. Inline, like I said, you can see here, it is a suggestion to the compiler. It's up to the compiler what it decides to inline it. It may heed your suggestion. It may decide to ignore it. It may decide to inline something you haven't indicated explicitly. The bit at the bottom sort of applies here. It's a little bit irksome. C++, if you do declare something to be inlined, say you're doing a class, and you had a few of the class methods that you wanted to be inlined, because they're small things and you think they're going to be called frequently. They have to be declared in the header file. They're not the type of thing that can be linked in. You have to declare them directly, because that then enables the compiler to insert them directly. As a suggested table here, you can see sort of call frequency going down and the method size going across the top. So if we have a large method, by large method we mean something more than 20 lines of code. And if you're looking at methods of several hundred lines of code, you're doing it wrong. So large method, 20 odd lines of code. If it's in the bottom grouping of call frequency, so this is the 80-20 rule. So this is roughly the large majority of methods we only call every once in a while. Large method, don't call it that frequently. There's no need to inline it. If it's medium, no need to inline it. If it's small, again, I would argue there's no need to inline it, but it's really up to you depending what you want to do. You're not going to see any significant change from inlining it. If it's a large method and it's called reasonably frequently, say 15-20% of the top methods, you probably don't need to inline it. Sure, you will save some execution time by inlining it, but the 20 odd lines of code itself is likely to result in a lot more CPU cycles than whatever the method call would have. And there's a danger that by inlining something that is called frequently at different points, you will notably increase the size of your code base. If it is a medium sized piece of code, and again it's medium frequency, if you wanted to, you could sort of say, can I remove any aspects from this, to look at the sort of the main path through it, and if so, inline it. If it's small and it's called frequency, you may as well just inline it. It's a good thing to do. You'll get an okay increase in speed, and with an okay, not particularly large increase in code size probably. For the methods you call frequently, top 5%, if you have a large method and you're calling that very frequently, it depends, but you probably would want them to look at that method and say, is there any opportunity to restructure things here? So again, this gets into the notion of the common path through it. What happens most of the times that you call it? Are there any exceptional things that only happen every once in a while within that? If you do have exceptional things, then that maybe gives you a chance to restructure, to rewrite, to break apart that method into things that are on the common path you do most frequently. They can be inlined, and then you have the odd exceptional thing you do once in a while. They can have a method called. Same applies then for medium size. And if it's a small chunk of code and you call it frequently, that's a no-brainer. Always should be inlined. Takeaways in this really rounds up our section on performance. A decent couple of sort of ones to round this off. So balanced design flexibility versus simplifying assumptions that increase efficiency. Sometimes you do need to increase efficiency, but invariably it is not free. You may increase the speed, that may have an impact on the size of it. It may limit the extensibility or the amount of flexibility that you have within it. It may make the code more difficult to understand. So it is always a balancing aspect. You need to ask, what benefit is there to optimizing this, and what am I losing as a consequence, and trying to get the best overall structure. Mantra, use a solution that's as simple as possible, and no simpler is generally a good one. So in terms of what we write and how we write it, that there is good merit, both from a design perspective and often from a performance perspective, to think about solutions, get a solution that solves the problem, be it an algorithm or our class structure or whatever. You need to solve it, yes, but then you want it to be a simple solution to that as you possibly can. Generally, that is a decent way of trying to make it efficient, or reasonably efficient. It's a decent way of making the class reasonably simple and potentially extensible as well.